Good afternoon, everybody. Welcome indeed to the next in the SESAR Talks, Innovation in Airspace Utilization. I'd like to welcome you to what I think is going to be a really exciting presentation with some very varied presentation from some top quality speakers. I think I'll start by explaining what this session is not. It's not a generic talk through everything that's going on in European airspace utilization. It's an insight into some examples of where SESAR research is contributing to an evolution in airspace use in existing and new environments. To start off with, we'll start in what might be considered a conventional air traffic management environment, but with the application of innovative procedures and the use of technology. Then we'll start going to a new and evolving aviation environment, very low-level airspace, to have a look at one of the significant issues holding up full drone operations. And finally, we'll move to the other extreme of the airspace, to the very boundary of outer space, to examine another new aviation environment, higher airspace operations. This is very timely, as the European Commission, with the help of the SJU, Eurocontrol and others, is currently producing a roadmap for enabling higher airspace operations, and it's hoped this will be published in a month or two. I'm Robin Garrity. I'm the Senior External Affairs Officer for from the SESAR Joint Undertaking, and I'll be your guide and moderator today. I welcome you to this presentation. So I'd like now to give you a little bit more information about what we have in store for you today. We have our four speakers, and the agenda. Sorry, we'll need to somebody. There we go. Okay, so we have first of all, we'll be looking at dynamic TMA and extended TMA for advanced optimized descent operations. This will showcase SESAR's work on introducing dynamicity in the application of RMP route structures in order to increase the flexibility of TMA operations. Then we start looking at an integrated common altitude reference system for drones and general aviation. Will be presented the SESAR use-based project Icarus, a project that sets out to provide an integrated common altitude reference system for drones and general aviation, thus addressing an important obstacle to enabling drone operations. And then we'll look at higher airspace operations with the SESAR exploratory research project ECHO, European Concept for Higher Airspace Operations. This aims to deliver a comprehensive concept of operations for higher airspace operations, building on a detailed demand analysis with the objective of allowing safe, efficient and scalable operations above flight levels where conventional air traffic operates. Then we'll have a panel discussion where you'll be able to ask your questions of the panelists, and I shall moderate this for you. Now, just so that you know how to do this, you'll see on your Livestorm stage a tab marked questions. Please type your questions on that tab. Note not the chat. The chat is just that. It's a chat between people who are present, and the questions are there for you to be able to pose questions to one or more of the panelists, and we'll do our best to answer them during the panel session as we can towards at the end. It's possible, of course, we'll have too many questions. What we will be doing, though, is recording all of these questions, and we'll make them available afterwards with written answers provided by the panelists. So hopefully no question will go unanswered, and these will be available on the SESAR Joint Undertaking website after the event, after a few days. So I'd like to introduce you to our speakers. Our second presentation today will be presented by Alberto Manella and Corrado Orsini. Alberto is a telecommunications than 15 years of experience in the aerospace and ICT sectors, with deep knowledge in GNSS downstream applications and unmanned aircraft systems. He co-founded TopView in late 2013 as a dream coming from his strong passion for drones and remote control airplanes, long before their mass market introduction. Today, he covers the role of innovation manager in TopView. And he will be supported by Corrado Orsini, who is an aeronautical engineer with a second-level master in satellite systems and services. He works in Telespazio as a technical manager of UAS-focused R&D projects Icarus and Aura. He is a developer of innovative solutions and services for the UAS world with focus on new space services. Our final presentation will be given by Mark Vallis he's the Senior Vice President, Space Programs and Dassault Aviation. I'll introduce him just before his presentation at the end. But first, I'd like to introduce you to Bruno Favrenek. Bruno is an ATM expert at Eurocontrol's Innovation Division. He has been involved in ATM research for 30 years, working on subjects ranging from early MODES data link trials to ASAS, arrival management and innovative arrival procedures. He has been involved in SESAR since the start of the program in projects dealing with the concept validation through fast and real-time simulations. More recently, he joined the SESAR Project 01, Enhanced Arrivals and Departures, leading a thread of work studying the dynamic deployment of arrival route structures. Bruno, the floor is yours.
Thank you, Robin. Sharing my screen. Okay. So the topic I'll be addressing today in this presentation, dynamic TMA, and more particularly adapting to arrival traffic variations. I hope everyone can see my screen because I see a gray one instead.
Yeah, we cannot see your screen, Bruno.
Oh, okay. I share differently then, perhaps. Share screen. Sorry about that. Small technical glitch. It's okay. Doesn't seem to work. Strange.
Okay, I've got your presentation here. If you like, I'll share it. And you just tell me.
Final try, and we'll see. Normally, I show different.
Okay. Oh, that's good. We've got you.
Okay, I'm trying to go full screen then.
Mm-hmm.
Well, it's full screen on my display, but it's not on. Well, that's strange. Okay. Seems I cannot go full screen then. Oh, why?
Okay. Would you like me to do it for you?
If you don't
mind.
Better.
That's good.
Yeah. Okay. So I'll stop sharing.
Okay, I will share the screen for you, and you just tell me when to click on. And okay, you should now see the full screen. Can everyone see the full screen?
Thanks, Robin. Okay, so
okay.
This subject of dynamic TMA, and more particularly adapting to arrival traffic variations, I'll be presenting this topic. Actually, the way we started investigating it in SESAR 2020 Project 1, as Robin mentioned. Next slide, please. And okay, historically, I guess everyone knows these kind of pictures. Historically, vectoring has been used in the terminal areas to stream and sequence traffic towards the runway. It's a quite efficient method for ATC, for air traffic control. However, it's quite demanding in terms of workload for the controllers, in terms of radio frequency load, and also it actually doesn't have a very good efficiency in terms of vertical profiles and environmental impact. That's something that's still operation in some places. However, in the recent years, next slide, please, there has been an effort to deploy performance-based navigation procedures, PBN procedures, with the advent of AirNav. You can see here another famous example. This is namely the Frankfurt area, where in the late 90s, what we call trombone routes, trombone procedures have been deployed. Actually, the idea is to take advantage from performance-based navigation, and more particularly its accuracy and repeatability to actually improve air traffic control impact. However, as you can see it, the idea in dense areas is to make sure that you embed in the procedure fast stretching capabilities to deal with arrival traffic and to sequence traffic towards the runway. As a result, it's still something that brings benefits, but it's capacity oriented, and there are still issues with the environmental impact and the fuel efficiency. Next slide. So where can we go from there? We've seen that with PBN, there has been an installation of systematic or systemized TMAs. However, the traffic needs to be streamed into the resource structure. This means that there are specific constraints to be applied to this traffic. And also the constraints are the same, whatever the traffic conditions, be it high, a peak, or being a low traffic. And we have a fixed structure with a fixed trade-off between performance area, for example, capacity versus flight efficiency or environmental impact. The question is, how and where could we introduce more flexibility? How and where could we introduce dynamicity? Next slide. And actually, first of all, is there room for dynamicity? As you can see in this diagram, it's a statistical view for the top 27 European airports in the terminal area of the yearly variation of additional times. What we call additional times is the extra flight time needed for sequencing, measuring, and ultimately, if required, holding in the terminal area. And you can see that there are a number of airports where the values may be sometimes high. And indeed, if you take the example of London Heathrow, as is highlighted here, you've got, for instance, 50%. In 50% of the case, you have a span of 7 minutes for this additional time. And if you take the full range, then it's from 0 to 20 minutes. This means that indeed there is actually viability, and then there is room for this dynamicity. Once we have said that, we could, the next step then would be to figure out how we could do something. Next slide, please. Let me take the example of point merge route structure. For those of you who are not familiar with this, the idea behind point merge, which is actually a fixed PBN procedure that has been deployed in about 28 places around the world now. The idea is first, instead of merging towards the runway axis, it's to merge toward the point prior to the axis, then a final segment joining the axis. And before that, sequencing legs in the forms of arcs at isodistance from the merge point that can accommodate path stretching when needed. This means that in this diagram on the left-hand side, you can see two flows of traffic to be merged towards the merge point. Whenever aircraft do arrive at the entry points, if there is not much traffic, they can go direct to the merge point. If there is some traffic and you need some sequencing actions, then the sequencing legs can accommodate this path stretching. It's very simple because of this isodistance property. Once the previous aircraft already on course to the merge point has reached a sufficient distance, then separation is ensured and you can direct the next one towards the merge point and so on. It's also actually, why did I choose this example? It's also actually exhibiting directly the relationship with the key performance areas, with the KPAs, and the trade-off between those KPAs. Of course, you can imagine the longer your sequencing legs, clearly, the more capacity you will have to absorb these additional times in the terminal area. But at the same time, because in that example, the sequencing legs are parallel and they are not laterally separated, you need vertical separation between those. This means vertical constraints in that part. And after that, because the distance to the runway is known by the FMS, you can engage into a continuous descent. So the price to pay when there is traffic is these vertical constraints along the sequencing legs. And once you are directed to the merge point, you can engage in that CDO. So the longer this legs, the more capacity you have, but the more impact on the vertical profiles you will have before you engage into a CDO. And then the longer the trajectory from the sequencing legs to the merge point, then the more opportunity or the longer the CDO will be. But on the other hand, the less flexibility will be available for air traffic control in sequence changes and things like that. Next slide, please. So this is interesting, but it's still a fixed structure with a fixed trade-off. When you want to deploy point merge in some place, then you need to have a look at the type of traffic you will expect, the capacity you will be requiring, and stuff like that, and you end up with a fixed design. But now there is actually a scalability, intrinsically a scalability in that structure, in the sense that, as I said, the longer the sequencing legs, the better, the larger the capacity we have, and smaller legs will end up with less capacity. But as you can see on these diagrams, you can actually reduce the length of the sequencing legs if you don't need that much capacity, and up with a partial overlap, meaning that the vertical constraints will be applied for less time along the sequencing legs. And then eventually you can even imagine a full dissociation if you don't need that much capacity, in which case you can relieve most of those vertical constraints and have better vertical profile with a better fuel efficiency and a better environmental impact. So this illustrates a kind of dynamicity, the type of dynamicity that we could be envisaging in the future. Why did I choose point merge? Just because it's more illustrative in the sense that the design clearly and directly exhibits those KPIs and this flexibility, this dynamicity property. Next slide, please. So the motivations here clearly as to depart from those fixed arrival routes and fixed trade-offs between the performance areas, so that we can imagine that we could have agile responses to arrival traffic variations in the terminal area. Deploying route structure in a dynamic way then would enable a trade-off at any time between those KPIs, meaning capacity when it's needed during peak hours, and more environmental friendly and fuel efficient operations when there is less traffic demand and you need less capacity. Next slide, please. From there, the idea then is that we could imagine that we identify somehow operating regimes in the TMA, and that each of these operating regimes would be associated with a particular instance of the route structure. So what we did in PJ1, in project 1, is start looking at the identification and characterization of such operating regimes. And we started with using data science on a large sample of traffic on a set of selected European airports, and started trying to have a temporal clustering of the additional times, trajectories and additional times in the TMA. As you can see here on the left-hand side, this is an example with Dublin, runway 28. The blue line, the blue curve, is the additional time, and the step curve is actually the identified clusters, categories of trajectories corresponding to these additional times. On the right-hand side, you can see the illustration on the 2D trajectories. Sorry, can you come back to the Dublin one, the previous slide? Thanks. Sorry. Thanks. And it's clear, in fact, Dublin has implemented point merge, so it brings me back to my previous example, has implemented point merge since 2012. As you can see here, when you've got a low traffic situation, a number of direct routes can be implemented. But then when traffic rises, you can see on the top right corner a diagram with traffic starting utilizing the sequencing legs in Dublin, and then on the lower left corner, a bit more use of those legs with a small overlap. And in the end, on the lower right corner, you can see that when you've got a lot of traffic, not only are you using the full length of the sequencing legs, but also the holding stacks. another example, though. So it gives a flavor of the type of regimes, but also the type of trajectories or procedures that could be associated with each of these regimes. I've got another example here with London, I believe, the next slide. So it's similar. You've got a distribution of additional times, identification of clusters, and then you end up with various regimes. And you can switch to the next one, Robin Sachs. So eventually, what we did in this initial study is to start from this temporal clustering in a statistical manner, purely statistical manner. And then we added some stability assumptions in relation with simple operation requirements, such as the need to ensure that you do not switch too often between regimes, between different root structures. And we ended up with identifying the possibility for operating regimes to be defined in airports with high and moderate variability of air traffic demand. In the end, we identified that there would be a need for 3 or 4 regimes to properly balance discrimination and acceptability. And next one. As a conclusion and a perspective, perhaps, what I just showed you, dynamic root structures may be understood as an intermediate step between the initial fixed root structures that were introduced with PBN in the terminal area, and on the other end of the scale, concepts such as tailored arrivals, where you have individually optimized routes for each arriving aircraft. So what we did is a kind of a revisiting and also clear mapping with arrival management, in the sense that we could imagine deploying dynamicity in TMA for sequencing and merging to final, or deploy it in extended TMA upstream to absorb variability and streaming traffic to a fixed downstream structure that would be more efficient. Or it could be a mix of the two. In terms of enablers, we have identified that existing ATFCM tools that predict the traffic load would be sufficient in the first stage to identify the time to trigger the transition towards a given route structure. And still open subjects, the acceptability and feasibility in terms of, for instance, publication of procedures, FMS capability, the link with the target times of arrival concepts, but also in the future, perhaps better predictions to identify when we need to switch between structures, including the weather impact. And that's all from my side. Thanks for your attention.
Thank you very much, Bruno, for that exciting insight into the future that awaits for us in extended TMA. I'm particularly looking forward to seeing how this analysis can help us to support the absorption of delay in route and in the TMA with this more dynamic way of feeding the information back to the wider air traffic management environment. So watch that one with interest. Thank you very much indeed. So at this point, I'd like now to move on to our second presentation, which will be taking a completely different chunk of airspace now. We're going to go right down to the weeds, almost literally, and look at the airspace, the very low level airspace now with project Icarus. And I'd like now to hand over to the two gentlemen whose bios I read to you just before the previous presentation. So I'd like to hand over to Corrado Orsini from Telespazio and Alberto Manella from Top View. Gentlemen, the floor is yours.
Thank you. Thank you, Robin. I try to share my screen. Let me know if you can see our presentation.
Yes, it's clear.
Okay, perfect. So good afternoon to all listeners and welcome to the Icarus project presentation. Today, my colleague Alberto and I will talk to you about these challenging projects. Why did I say challenging? Because the challenge is inside the name Icarus, Integrated Common Altitude Reference System for Uspace. Icarus projects proposes an innovative and feasible solution to address the novel challenge of the Common Altitude Reference System inside the very low-level airspace, with the definition of a new Uspace prototype service with its validation in a real operational environment. But before starting with the project, we asked ourselves, if something works, why we should break it? Why should we change the way the altitude is calculated? Barometric altimetry has been the preferred way to ensure the vertical separation for almost 100 years in manned aviation, and it works. So we thought maybe it's time to revisit. New technologies are born and are available and usable. So we tried to provide the answer to all the previous questions with an innovative idea. Define a universal flight altitude reference system based on GNSS and provide a new U3 Uspace functionality, giving real-time information on the vertical distance to ground and the conversion of different altitude reference system from the barometric one to the geometric and vice versa. But why Icarus? With the forthcoming increasing of the drone usage in our skies, in the next few years, there will be the need of more precise height measurements to ensure that the drone traffic and the manned traffic will be separate. And the barometric measurements are not very reliable at the very low level, especially over cities. We know that there are three methods of determining the altitude of an aircraft based on the pressure difference with respect to unknown datum, that are the QFA, the QNH, and the flight level. All of these three methods are based on pressure difference. But we know that drones can take off and landing almost everywhere, and especially in the near future, with the advent of the urban air mobility, the limitation for the use of the barometric approach in the very low level airspace opens to this new challenge. In fact, the atmospheric pressure over cities is difficult to measure due to the high temperature gradients. We know that buildings generally radiate heat. Air pressure is not constant over time. So the regional QNH does as well. So drones may need to be able to change their QNH setting during the flight. And finally, the certified resolution of the barometric measurements in the airplanes is 25 feet, which is very coarse to be used in the very low level airspace. So with its proposal and its work, Icarus will enhance the vertical separation and will enable the high density operation. But more in detail, what is Icarus? Icarus can be conceived as a U3 Uspace service to be distributed to the end user, manned and also unmanned pilots, providing UAS common altitude reference at the very low level, UAS ground obstacle awareness at the very low level, and UAS manned common altitude flight reference. The starting and focal point is that the height is calculated by GNSS. In particular, using the WJS84 ellipsoid datum as standard reference system to provide a common zero altitude to drones and manned aircraft that flies in the very low level airspace. More in detail, let's see now the three objectives. The first one that we analyze is define the technical requirements for the high accuracy GNSS-based altitude measurements for drones to allow a reliable and accurate common vertical reference. So we analyzed the dual frequency multi-constellation GNSS receivers requirements for the definition of the main navigation parameters. We analyzed the GNSS signal integrity in order to identify possible strategies for the monitoring of the GNSS signal. And finally, the added value offered by the GNSS Galileo constellation. In the second objective, we investigated the vertical accuracy and resolution that are achievable by the actual DTM and DSM services. with respect to the geodetic WJS84 datum. We analyze which DTM and DSM available model could be used during the strategic and also the tactical phases of the flight in order to have a situational awareness of what is surrounding drones. But also we analyze the transformation error introduced by the DTM and DSM services with respect to the WJS84 datum. Moreover, it's a new proposal, a Gnss, geocentric altitude mandatory zone, that are very small zones in which is mandatory to use the WJS84 datum as a standard reference for the altitude. And finally, in the third objective, we designed a tailored use-space services for the altitude translation between the geometric to barometric altitude, also for UAS and manned aircraft. So we have analyzed the translation model, defining the input and output parameters, the actor involved, also the communication strategies for the delivery of this service, and finally, the error introduced by this translation from the barometric one to the geometric. Now I give the floor to Alberto.
Okay, so thank you, Corrado, for your introduction. Yes, I will give you here some more details about the Icarus service architecture. So in this slide, you can see actually a simplified version of Icarus service architecture. In the middle of the slide, you can see the actual Icarus service, so the core engine of the service, that is fed by different input. And the output that the service will produce will be the vertical conversion service and the vertical alert and information service. So these two outputs will be delivered by means of an application program interface to possibly to different use-space service providers and to the drone users and the manned aviation users. We believe that for drone user, the new mechanism of communication, such as the 5G technology or even satellite technology for remote areas, could be useful for delivering this information. While on the manned aviation, we are, of course, more conservative, and we believe that the VHF as consolidated mechanism could be useful to disseminate this information to these users. As you can see, the service is fed by different input, which are mainly the GNSS, so the status of the constellation, the monitoring of the GNSS infrastructure on ground, but also all the geographical information services, especially for the DTM and the DSM that Corrado just mentioned, but also for the ground obstacles awareness. So we believe that a large database of these elements will definitely feed the service for ground obstacle awareness. And finally, we need one unique certified barometric pressure service provider, because this information is useful to calculate dynamically the offset between the WGS84 datum, which is a geometric information, and the barometric information that, of course, is variable considering the day. Next slide, please. In this slide, we have proposed a placement for Icarus service, so a U3 use-space service that you can see in yellow on the right side of the slide, so the altitude translation service. And this service will interact with many existing and planned use-space services, such as the navigation infrastructure monitoring service that I just mentioned, but also the navigation coverage and information, and most of all, above all, the tracking service that will be very important to feed the Icarus service, because we need to know the information about position of drones with their reference system, and we have to elaborate this information to be disseminated to the other users. In the next slide, there's a methodology, the methodology that we are following in this project. Actually, we are almost at the middle of the project. We started from the previous Airspace projects, so we started from the requirements that have been defined by Icarus, Dreams, Diode, but also other concurrent projects such as Gov 2.0, with existing studies from Eurocontrols, and also involving a number of experts in the advisory board that helped us to shape this concept. And now in this phase, we are in the definition of architecture, and we started to implement the service. And in the next month, we will finalize our application program interface that will be validated by the involvement of two Airspace service providers, so the Italian Airspace service provider and the Polish Airspace service provider, with the different validation exercises in both simulated and real environment. In particular, for the general aviation users, we will use a cockpit simulator, actually a general aviation Cessna scale 1-to-1 cockpit that will be used to show this information, to present this information to pilots in the way that they are used to read this, the typical information on capsule instrument or on different avionics, while on the other hand, drone pilots will exploit this information by means of their ground stations, the typical ground station. At the end of these exercises, we will have a consolidation of our concept and a final concept of operation with the lesson learned and recommendation. In the next slide, we just reported some relevant use cases that will help us to validate the concept. So we started, just to mention, the actual state-of-the-art operation with drones on the left. So the first use case, which is about industrial ski lift inspections. But we are considering also the new scenarios that would be probably presented with the advent of the urban air mobility, so drone taxi, goods delivery by drones. And in the final use case, we will present an airport vertiport passenger transfer. And in these particular use cases, different airspaces will be encountered by the drone taxi, and we will also present our proposal of geometric altitude mandatory zones that Corrado mentioned, and let's say all the requirements and capabilities that these drones must have to enter these new zones. So as a final recap, Icarus proposes a solution to solve the challenge of the common altitude reference system with a novel approach that will allow high-density drone operation, especially in the cities, where actually we cannot separate traffic vertically. We have to ensure, of course, the backward compatibility with the existing manned aviation. So for this reason, we introduce a vertical altitude translation service. And finally, the big number of drones can allow us to have a large data set to validate our concept. So in the next months, after we will finish our prototype service, we will start with the validation exercise. It's all by my side. I thank you all for your attention.
Thank you, Alberto, and thank you, Corrado, for a most interesting presentation. We're really starting to look at some of the questions that have emerged from the earliest stages of research, when the question of common altitude reference, still unanswered, was first raised. You have an innovative approach to solving this that may well have applicability in the future for manned aviation, if there is ever a transition from general from barometric to geometric altitude air traffic management. So I'm watching with great interest how your development of the service can work, and in practicality terms, how successful it can be. Thank you very much once again for a very interesting presentation. So now it gives me great pleasure to introduce my my last speaker.
Oops. Looks like we have lost Robin. So maybe I will present myself. So I'm Marc Vallès from Dassault Aviation, and I'm the director for space programs. And I will have the opportunity now to present you a program which is currently running in the frame of SESAR, led by Eurocontrol, which is called ECHO. So I go and take the lead. Can you see my screen? Is it okay? I have no feedback. Yes, okay. So ECHO is the acronym for the European Concept for Higher Airspace Operation. And these programs is really trying to reply to a new demand. And because we have so many different types of vehicles and objects which are now trying to occupy, move, and work in the higher airspace. So we have identified that it is really needed to have a look on how to include all those type of known and sometimes only planned vehicles and related operations in order to enable in the near term for the beginning and then the future operation in this higher airspace in a safe and orderly manner. So in particular, we would like to be sure that there is an efficient interaction with the current air traffic management, but also with the space traffic management, which is currently under scrutiny and sometimes even under studies at international level, because the space traffic management cannot be a national matter. It must be only an international one. So the project is made in a way to be sure that we don't forget anything. So there is a first phase of research analysis in order to take into account all the studies which has been performed in the past, to have a look on what are the vehicles and the operations which have already been tested sometimes, and what are the ones which are foreseen. And the next step, so it's still running, but we are coming to the end of this preliminary phases, which allows to identify what we are talking about. And then we are now in translation of all this in a demand analysis based on all the types of vehicles, categories of operation that we have to take into account. And at the end of the project, we foresee to be able to deliver a concept of operation which can be the input for the next steps for an ATM improvement in order to take into account those newcomers. So the categories of the aerospace system. So in fact, the main characterization is that there is it's not a single problem. It's a sum of lot of different situations, because we have huge range of flight speed, from very, very low speed for balloons, for example, and very, very high speed for vehicles which are coming back from orbit, which are Mach 25, or maybe we can talk even in kilometers per hour. The flight durations also are very different in terms of range. Some flights are very short, some are very, very long. It's a matter of sometimes months So we have flights from minutes to cross the Earth and sometimes months of operation. Of course, the maneuverabilities of those vehicles are completely different if you are talking with very almost not powered, depending from the weather conditions, to a rocket engine propulsed vehicle. The maneuverability and the speed is not the same at all. The atmospheric environment also is not the same, even if we are talking of higher airspace. The variation of the density of atmosphere is huge. Just I think it's interesting to recall that the drone Ingenuity on Mars, it's very interesting to see, but on ground on Mars you have more or less atmospheric pressure that exists at 30 kilometers on Earth, and you see how it's difficult to have a kind of an helicopter or a drone flying in such a thin atmosphere. But on the other side, the fact that the atmosphere is very thin allows to have a very, very high speed of several kilometers per second. And we will see that later. And then the traffic conditions, of course, are not the same for several reasons. And one is the relative difference of speed, which can occur in some portions, in some volumes of the airspace. And the other one is mainly because there are routes also, or there are locations for the type of application. So we know, for example, that the balloons, they have some difficulties to fly in some regions because they don't have the winds which allow them to be manageable. So a lot of things occurs which are making this very, very complex. So we will not enter in this presentation, which is trying to give a picture of all those type of vehicle, but I invite you to take a look on that, because there will be a presentation made directly by the French Direction Générale de l'Aviation Civile. It will be virtual, not anymore in Dubai, but maybe in Dubai, we don't know yet. At the next International Astronomical Congress, so it will be at the end of October. So this will be presented. But what is important, I think, is to understand that today we are using only a very small portion of the atmosphere, and there is more which can be fly in, and then above that, of course, we have the space by itself. But we'll have to manage in this area and the vehicles which are coming from Earth, from ground, the vehicles which are sometimes for weeks or months in the stratosphere, and some vehicles which are coming back from space, all this in the same situation. So this is first identification of the main higher airspace users that we have collected from now. So I will not enter in the detail of all of them, but you can understand that in fact some of them are, as I said, more or less local, very low, and standing for a long time. Some of them, like the one we just have seen, like the A2A suborbital vehicles, do have exactly the same type of profile, flight profile than weapons, than blue sky hypersonic weapons. So it's clear to understand that without air traffic management, without clear air traffic management, it will not be possible to safely operate this kind of vehicles. It's not only a collision matter, it's really a matter of management of airspace. So what we can see with the colors there, that there are some applications which come before 2035, for which we have to think from now how to implement some means, some rules, some procedures in order to be able to have a safe introduction of those vehicles in the airspace. Some others will come probably after 2035, and there are some military applications for which some of them already there. But maybe we'll have to take care when we will merge the civilian and the civil use of the airspace, to be sure that all management of those areas are not only technically feasible, but also managed at a political level, at international level. So some considerations about the physical limits of the flight domains are important because there are some laws of physics which are constraining and linking also the speed, altitude, and communication. For example, there is a mechanical and thermal structural limit which does not allow you any vehicle to survive to the speed when you are too fast in the air density, because you melt. So there is no material in the universe that can survive those temperatures. So it's not feasible to be faster than what is shown this on the mechanical thermal structural limit. Then you have an aerobic corridor, which is, at the contrary, there is not enough oxygen in the atmosphere to allow to have the energy that allow you to have some motorization, so some propulsion. So it's not very strong, but it is still a barrier. And you have also, for us, for the air traffic management, this radio blackout limit, which is directly linked to the temperature of the plasma which surround the vehicle when you go in a hypersonic mode. That does not allow, which does not allow to have a radio communication in a proper way, at least in on the sides, on the the sides where the plasma is there. So we tried to make a first type of categorization about what are the vehicles that we will have to manage for this in this study in order to prepare the CONOPS, and we have identified the supersonics are not there, but we have decided to add the supersonics because whatever they can, it's not more difficult, but I think it is important to consider them. So you see, we have the high altitude platform systems, which are low speed and, let's say, regional. Even if they can move, they don't move so quickly, so they can be managed at a certain speed. Then we have the aero launching to orbit, which go to space and come back to the same zone. So they are not low speed, but they are regional. And then we have what is called the A2B suborbital, or the lower stage of launchers, which are going to space much more for, I mean, the A2A suborbital today it's mainly recreational, let's say, it's space tourism, but it's also operational when we are talking of a lower stage of launchers, putting satellites in orbit. And those one, oops, I did not want to change. I don't know what's happening. What's happening? I don't know. Sorry for that. So I go back to where I was. Okay. So after that, we have the vehicles which are really moving very fast and very high, or because they are connecting two points on Earth, so the A2A suborbital, or because they are coming back from space. So those one are worldwide because they cross continents in few minutes, and they are at very, very high speed. So what is the topic of ECHO is to now translate the new needs in CONOPS and to propose some rules. So today the organization of ECHO is made of a mixed between institutional entities and private entities and operators. So the consortium also exchange with an advisory board, and we will exchange through workshops with enlarged community. So the next workshop is foreseen to be held in June, end of June this year, and it will be the opportunity to have a feedback about the collection of data that we have and the first identification of a vehicle on operation and the first identification of what can be the demand before going to translation in ConOps. And then we will have another workshop, which will be in January 2022, which will be an opportunity to check with the community, the general Aerospace community, the first elements that we have about the ConOps, the translation of the demand in preliminary ConOps. Of course, this activity, which is performed in the frame of Europe, has an international interest. So we are in link with the international organization, and there is also a task force which is running now in the ESA in order to address some of the topics, for example, the suborbital topics, and there are also some activities which are performed in the frame of the international communication ITU in order to deal with the allocation of bands, frequencies, and how to manage this at international level. So I was rather quick, but the interest is to depict you what is now going on. We don't have yet, we will have something to show at the workshop. We don't have yet, let's say, precise use cases. So we are working on some use cases which will allow us to propose the technical solutions that can be implemented in the air traffic management. So more or less, what I can say is that today we have collected the interest of a lot of European entities which has the opportunity to provide data about their plans, the vehicles they plan, or the results they had for tests and so on. And we are trying to also introduce some elements which are coming from non-European projects in order to be sure that our collection of data is sound enough in order to have a proposal which is not only a local solution or specific for Europe, but which can be a proposal for a general harmonization of the air traffic management, of course, in the frame of SESAR, but also with an international possibility to exchange, at least for the very high-speed vehicles, which are moving across boundaries and even across continents. That's it. I don't know if Robin is back.
I am back. Thank you very much, Mark. I do apologize for dropping out so suddenly, but it seems I had a bit of a network issue, but happily all seems to be resolved now. I hope you had a chance to introduce yourself, or would you like me to do that now in case people didn't know precisely who you were?
I just said that I'm Dassault.
You're Dassault. Oh, well, you know what? I'm going to read the bio because I think people will be interested in this. Forgive me for this slight alteration in the order of things, but I think it's only courteous to do this for you. Following your childhood in Africa, Mark has been alternatively working for national agencies and European industries, living in locales as different as New Caledonia, Guyana, Normandy, Toulouse, Rome, and Paris. Mark was lucky enough to play with all elements of European launchers family, Ariane, Soyuz, Vega, both in launch vehicle and ground segments. Starting in the space field as a test engineer of cryogenic rocket engines, he has worked as systems engineer, project manager, launch operation manager, head of production, strategy and business manager, and program manager. Today, Mark leads the space programs directorate of Dassault Aviation in Paris. Sorry I didn't get to say that earlier on, Mark, but I think it's a very interesting CV, and thank you very much for your presentation. I think one of your closing remarks was very important there, that you're saying you don't yet have results yet because it's very early in the project. I think that's something that needs to be borne in mind for all the presenters today, in that the work is relatively early in its gestation. Exercises and so on are still being organized. They have ideas about what they're going to research and how to do it, and the real conclusions come much later in the project. So it's one to watch, one to keep your eye on, but we don't yet know what the answers are going to be. That's the thing about research, and particularly in the case of the higher airspace operations, we're coming up with a ConOps here, a concept of operations. This is entirely new. In the past, we've had a relatively small number of vehicles doing their thing at very higher airspace. Now there seems to be a swathe of potential customers that are and businesses that are looking to use it, and it needs to be organized. And looking at the disparity in performance that Mark showed us earlier on in that rather complicated but rather interesting slide, it's not going to be able to be managed in the same way as we do air traffic control. So I think it's a very interesting project. Similarly, with the U-Space project, with Project Icarus, we are looking at adjusting what has been a fundamental tenet of manned aviation for a great period of time now, by introducing geometric altitude operationally, and maybe even a mixture with a conversion service. This, of course, requires research and will require as much hearts and minds as the science. So it's a very interesting research project which we've started to present to you today. And of course, Bruno presented something which is a little bit more mature. We're building it on some implementations, but there are some new ideas to introduce increased dynamicity into the airspace that will stretch further back, further away from the runway, that hopefully can increase predictability, reduce environmental impact. So these are all new things that are being brought and discussed, and showing that a full range of the kind of work that SESAR is doing. So thank you all very much for an interesting collection of presentations. I enjoyed them very much. I've learned things today, and I think that we should keep a close eye on these, and it may well be worth revisiting some or all of these later on. Thank you very much indeed. I'd like now to move on to our panel session. And we now have approximately half an hour, slightly less than half an hour, where we can attend some of the questions that have been asked, and a large number of questions have been asked. I'd like to start with you, Bruno, if I could. It is building, the project, as I mentioned a moment ago, is building on previous research and deployment into the point merge activities. I wonder if you could expand a little bit more on how you see this work really feeding into the wider air traffic management and the extended TMA and into the en route sector to increase predictability, reduce environmental impact, and so on. I think because we should always bear in mind we're not looking at this in a very just at the airport. This is a much bigger problem you're trying to solve.
Yeah, indeed. Actually, I mentioned point merge. It's more an example, it's illustration, but of course it's one possibility. And to answer your question, actually, most of the point merge existing implementations are in the TMA after the IAF. But there is at least one example in the Paris ACC where there is a point merge structure on the northwest feeding the Charles de Gaulle approach. So it's an excellent TMA point merge structure. And when it was put in place, the controllers noted that they had much less delays or management delays to absorb in a TMA. So it's already acting like a kind of a buffer, a capacity buffer that would we could imagine that we have, as I said, such structures in the excellent TMA, and then fixed routes in the TMA with more efficiency then.
Thank you very much, Bruno. I'd like to move now to Icarus. I think if we look at the Icarus concept, the idea of having these two different altitude references, which certainly in the case of barometric actually change with the pressure change across the day. I think there may be some considerable interest and questions asked about the reliability of any conversion service, the timeliness of it, and the effectiveness of being able to provide that to aviators with such accuracy that you can actually build separation on it. Have you got any thoughts about where that might go and how you could assure the quality?
Yes, Robin, and thank you for this interesting point about Icarus. Well, indeed, as also Corrado mentioned during his presentation, we have a non-reliable assessment and measurement of the barometric pressure, especially over the cities. So in this case, where most of the new business is expected, so the BV loss operations, drones deliveries, drone taxi and so on, we expect that we have to improve somehow the reliability of the measurement just to increase the numbers of operations and to move towards a more reliable solution. We believe that this sort of separation between two drones, among drones, is going to be technically a requirement of the receivers, because the GNSS receivers have already the geometric model inside, to do the calculation. What is missing is the model, the terrain of model, and the displacement of the ground obstacle that can be an hazard for BV loss operation, especially at very low level. So the point is how to translate this information to the manned aviation community. So in this case, we have thought about this translation service in order to maintain some sort of backward compatibility without forcing this community to change equipment on their planes and so on. And we have also to consider that the areas where we believe most of the traffic of drones is expected, especially over cities, is a sort of airspace that generally is not operated by general aviation flight. We might encounter helicopters during HAMS operation and so on, but we do not expect, general aviation flights flying for tourism. So we are trying to proposing this new approach, this new paradigm. Of course, as you mentioned, this is an R&D project. So we are proposing a solution, but we will need to validate the solution through different exercises before proposing something that can be also operative at the end. Corrado, I don't know if you want to add some points.
Thank you very much, Alberto. Nothing to add, Corrado?
No, I think it's
okay.
Alberto said almost everything. Okay.
Perfect. It's good to know. Thank you. And so then, to Mark, I'm kind of embarrassed to ask this question, but I think it has to be asked because it's uppermost on most people's minds when we start thinking about the higher airspace. It regards the upper boundary. In fact, the upper boundary of current airspace and the upper boundary of higher airspace. I know there's considerable talk about exactly what it is, the sovereignty issues, and who has the right to govern in this kind of airspace. But also, the base, are you looking at using fixed at 600 or 660, or are you going to go lower so you can bring business aviation into it? The vertical boundaries is a question I'd like to hear some thoughts about.
Yes, sure. In fact, as we want to introduce all those newcomers in the air traffic management, we prefer to have a large view and to accept that maybe there is not a strict frontier. In particular, as you said, even if the lower boundary is more or less harmonized in Europe, there are still differences between where is really the traffic and up to where the law applies. So today we try to take into account all what is flying above the flight level 450, something like this. I mean, to be sure that we don't forget the aircrafts which are in the upper side, not starting from the level 600. Anyhow, as I said, we try to propose some solutions which are not only available, usable in Europe, but we can share also with our colleagues at international level. So we cannot just block ourselves on a very fixed lower boundary. For what respects the upper boundary, it's even worse, if I can say, because today there is no real boundary. Physically, there is no, because the atmosphere is just rareifying very gradually, and in fact, there are some airspace or at least altitudes, let's call that altitudes, in which there is almost no vehicles, because there is too much drag to be a satellite for a while, because you fall down in few hours. But there is such a need of energy and speed that there is no interest today. There is no vehicles that stay in this area. So it's somewhere between the level of 150 kilometers up to 250 kilometers. This is an area in which the vehicles that are going there, they fall down on Earth, because whatever they cannot stay there for a long time. So nevertheless, sometimes there are debris. I mean, it could happen that there are some satellites coming back from space. So we have to manage, not really, let's say, a physical boundary made in altitude, but much more, we are looking to that. We are thinking that rather than talking in kilometers or meters, we should talk in speeds. So in kilometers per second, because there is a kind of bisection between the velocity at which you are and where you are for the upper boundary. So as I said, the balloons and the objects which are flying, whatever, they cannot go really above the 600 flight level. But for the others, which can fly without atmosphere, without oxygen, which are based on some other types of propulsion, there is this relation to speed is very important for us for the air traffic management. More or less, when you are not too fast, you can be identified by your location. But when you are starting to fly at several kilometers per second, then you are not just in location, you are at one speed, because this gives, in fact, also the maneuverability, the level of energy, the type of communication that you can have with others and with the ground, because of the Doppler effect and so on and so on. So in fact, we more and more we will see exactly what will be the results of the studies which are running now. But we have the feeling that above a certain level of altitude and of speed, which is related, the characterization of the objects, whatever they are, will be much more in speed than in location. I don't know if it answers to the question.
Thank you, Mark. It does, and many more besides. Thank you, very comprehensive. One thing that came out in your answer, but also in answers from the other presenters, and indeed from some of the questions we're receiving through, a common theme for all of your domains is GNSS. Now, I wish to ask a question to each of the presenters here, and I'll go round you in turn to answer this question, but from the perspective of your particular presentation. So the increased reliance on GNSS brings with it obviously a need for availability and continuity that is fairly serious, and yet we still must need to look at the fallback procedures or capability that will enable us to maintain safety in the event of any kind of GNSS failure. So I wonder, from these perspectives, if Bruno, you could talk about how that will affect the precision of the PBN procedures and the ability to survive such an eventuality. Alberto and Corrado, clearly you're now introducing the third dimension using geometric signals. So how would that survive a failure. And Mark, I don't know if it's relevant because I don't know enough about the subject, but you say you've got this communications blackout that's due to the plasma and what have you. Does that affect GNSS? Does the speeds you're talking about affect the usability of GNSS? Any of these new criteria, do they require additional thinking to the traditional thinking on GNSS? So maybe I could start with Bruno.
Yes, thanks, Robin. Indeed, GNSS availability, continuity of service, and so on, they do not only apply to the dynamic aspects that I mentioned, but already when you start deploying PBN procedures and have. And from that perspective, any procedure in the TMA, or user, I guess, even in Aerospace, any procedure in the TMA needs to make provision for a fallback in case of navigation means failure, be it for a single aircraft or be it for the whole traffic affecting the whole area. So, for instance, in the case of because of point merge, the recommendation is that there may be a need to revert to vectors in the area, and maybe if this happens during a peak of traffic, there will be a need to coordinate with flow management, reduce capacity, and so on, depending on the duration. But this has to be embedded in the publication, provisioned and studied before, including a safety study.
Thank you, Bruno. Alberto and Corrado.
Okay, Corrado, you want me to start first, or you want to?
Okay. Go.
Okay. Okay. GNSS for us is a compulsory part of the study, and yes, we have to understand the requirements for in particular we are making some testing experimentation not only with Gnss but also with the dual frequency multi-constellation receivers, exploiting also the added value of the new benefit provided by the European constellation Galileo, which may also provide new benefits such as the authentication service, which may limit the spoofing attempt and all the cyber security mechanism that can be a threat, especially in the cities. However, we believe that the combination of GNSS plus other technologies on board the drone may help in the event of an outage or a failure of the system. So the concept of integrated navigation with different sensors on board, which are getting more and more miniaturized, such as IMU, LIDAR, but also visual system, but also maybe exploiting some opportunity signal from the terrestrial network. We believe that all this combination may help in case of non-nominal situation with drone flight, especially at during BVLOS operations.
And if I may, we are doing our projects, ground service to provide integrity calculation and also an augmentation service to drones and drone pilots in order to have a monitoring of the signal degradation, GNSS signal degradation, and also its integrity. So maybe it's also possible to make a forecast of GNSS performances. So we thought that using a hybrid approach with other sensor and also a ground service, we could be limited the effect of GNSS degradation.
And
thank you very much indeed.
And if I may add just one small detail, with the use of 3 constellations, also of Galileo, we are achieving very good results also on the vertical axis. So not only on the horizontal plane, but very, very good accuracies also on the Z-axis. And we believe this is an important outcome so far.
That's good to know, given the subject of your research. Thank you. So finally, Mark, please.
Yes, so first of all, this effect with the plasma blackout appears only for the very high-speed vehicles. So as I said, we have in the higher airspace all the classical vehicles, I mean classical, or low or going up to supersonic, below the Mach 5 barrier. So for all those, the matter is exactly the same that for my colleagues. So I think that we are entering in a new era in which really the GNSS will provide some solutions that can be available and secure enough. For what regards the very high supersonic vehicles, the plasma appears on the intrado, which is toward Earth. So it means that we have a problem of radio communication, radio localization, and radar, and so on, towards Earth. But if looking towards the stars, I mean towards the satellites, in fact, we keep the connectivity. So this allows not only to correctly use GNSS, all the PNT positioning, navigation, and tracking system, and timing, and also communication. So very probably those vehicles will also have some data links, some communications toward the ground segments during en route, or also towards airports through satellites rather than through direct connection with the ground telecommunication services. This is why we fully believe that there is a real interest for the European community to go to this proposal of sovereign telecommunication constellation, which is under proposal today by the DG DEFI, I mean, which is the Commissioner Thierry Breton is pushing a lot for this investment, this infrastructure to be developed in Europe in order not to be fully dependent to the American solutions, which are currently developed by Starlink. Even today, if we have OneWeb in the coming times, they are not fitted with all the type of sensors and capabilities that we should need in order to have a relevant sovereign telecommunication system for Europe.
Thank you, Mark. And thank you all for answering that question. Before I move on to the next question, I need to tell all members of the audience, and thank you very much for staying with us. If you look at your live Storm platform, you'll see at the top of where the chat and so on is, there's a tab marked polls. In the polls button, you'll find a few short questions just so that we can gather your feedback from the event. If you would be able to take just a couple of moments to have a look at that and make your appropriate sections, we'd be most grateful. It would help us to improve the events for future events. Thank you. I have another question for all of you, actually. We've been talking very much now here about VLL or higher airspace, or shall I say conventional airspace to keep it straightforward. But in fact, we all know airspace is one continuum, and virtually all vehicles transit through one or more of them. And so therefore, do we actually need the same management system to be applicable to all of them, or can we have different systems completely that interface somehow, or something in between? And how are we best going to create this harmonized aviation management system that enables all of these very different environments to work together safely and effectively? This time I'd like to start with Mark. Would you mind?
Yes, thanks for this question. So we are still at the beginning, because we are making the inventory of what can be the demand, but it seems that there will be some functionalities that can be performed just by evolution of the specification of the current system in order to take into account those specificities, the use case that will be identified in the ConOps. And second, probably there will be the need for some additional functions. As we said, for example, this communication, which is not a direct communication, but a communication which is going from somewhere else. on the use of Gnss as a reference for several functions. And for some cases, it appears that maybe we will have to develop some new system to be implemented in the air traffic management, and in particular, if we want to try to merge real time in operation the space traffic management and the air traffic management. Today there are bricks which are missing. So I think that for this type of application, there will be the need for the development of new systems.
Thank you, Mark. Alberto Corrado?
If I may, Alberto, we thought that we are in an early stage, and as said by Mark, there is the need of new standard to define new standards also for the GNSS, for the DTM, DSM models to be provided to the users, and also regarding the QNH, as stated by Alberto, that we need to define a standard regarding the all these data translation and all these, let me say, to provide this type of data. So we need a certification. We need to define a standard, but important, we thought that it's to start with the research.
Yes, indeed. We need new standards, but if I may, I would only suggest to consider lighter standards, of course, for drones instead of the one we are used for the traditional manned aviation. We don't have to, let's say, to kill a business opportunity, a new economy that is growing. So, with respect to safety, of course, we have to prove on field how the system are reliable, but we should also cope with the lighter standards in order to maintain still the economical benefits of drones.
Thank you, Alberto Corrado. Bruno, briefly, please.
Yes, I guess it may depend from my perspective on the type of vehicles. I mean, for the dynamic aspects or the other management principles, you may have to apply this in shared airspace if you take into account, for instance, future large cargo drones that may be operating from an airport where there is a lot of traffic. Or it could be that you try to apply the same principles to other platforms like, air taxi. Then maybe you want to implement some kind of driver management and dynamicity in the procedures, perhaps. So there is room for that, for sharing principles and rules, perhaps.
Fantastic. So, well, I think we're all at a very exciting stage with such fundamental changes coming up. I think we're now approaching the very end, and it's time for me to draw this to a close. Just to remind everybody that in fact we have been answering the questions as best we can on the side panel of the platform. What we will do is we will record these questions, and any that we haven't been able to answer, share these with the presenters, and we will publish these answers on the SJU website in a few days or next week or so, and this will enable you to see the results of the questions. Just in summing up before we close, what we presented today was an insight into some of the projects that are being managed through SESAR to show how there are innovative uses of airspace utilization, but not just in the airspace that we are most familiar with, but also in a new lower down band of airspace and this seemingly enormous and largely untapped volume of airspace above where conventional aircraft typically fly. There's a lot of work to be done, political, scientific, operational, and I think these projects in their relatively early stages have already demonstrated that we have some very interesting ideas. Please check these projects out and our other related projects on the SESAR website, and of course look out also for future webinars where we will touch on other related issues. It's been my great pleasure to be your host for today, and largely operationally focused area, and as a former controller, I love talking more operationally than pure technical. So thank you all very much for attending, and all that remains for me to do is to say a big thank you to our presenters, to Alberto, to Corrado, to Mark, and to Bruno for sparing your valuable time to give us your insight into your projects that are working very excitedly towards this great new future. Thank you all very much indeed, and I wish you all the very blessed of evenings, and stay well, stay healthy. Thank you, everybody.
Thank you.
Thank you. Thank you all. Thank you, Robin.
Bye-bye.
Thank you, Robin.
Bye.